So for today's lecture, we'll be doing another technique of integration. It's called integration by partial fractions. Okay, so for this technique, the integrand will be rational expressions. Particularly, you have uh, polynomial in the numerator over polynomial on the denominator. Okay, but of course, there will be some cases where you have a rational expression, but it's not polynomial over polynomial. Okay, but there will be a way to rewrite that expression into something polynomial over polynomial, and therefore you will be able to use this method. Okay, so let's start the discussion. So for example, let us consider this sum of rational expressions. You have here 2 over x minus 2 plus 3 over x plus 1. Okay? So we can combine this into a single rational expression by doing the addition of fractions. So I hope you remember that. So if not, just try to recall how to add or subtract fractions. So same method will be used. Okay. So suppose we combine them into a single rational expression, we will have this, or it can be simplified into the following. Okay, especially the numerator, you can simplify it as 5x minus 4. And then on the denominator, you multiply it. Okay. Now, if I ask you to integrate this expression here, as it is, it's not easily integrable. Okay? As it is, it's not easily integrable. Okay? However, knowing that this expression can be written this way, okay, you can rewrite that expression into this way. So you will now integrate this sum. Okay? And these two guys here, you can integrate easily. This is just constant over a linear expression. Similarly for this. And these are here, when you integrate, will become um, logarithmic functions. Okay? So in here, if you integrate, you'll just get 2 ln of x minus 2 plus 3 ln of x plus 1 plus the arbitrary constant c. Okay? We call this guy here the partial fraction representation of this expression. So at this point, you should realize what we're going to do. If we have something like this expression, we want to decompose it into partial fractions. Okay? Well, we want that the decomposition into partial fractions can be integrated easily. Okay? So, suppose we have polynomials f and g, and suppose the degree of the polynomial f is less than the degree of the polynomial g. Okay? Then we say that the rational function f of x over g of x, we say it is proper. So the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. Okay, so this is an example of proper rational function. The degree of the constant functions, it's just 0. And then the linear function, the degree is 1. So this is a rational, this is a proper rational function. Similarly for this. In here, the degree in the numerator, it's 1. The degree on the denominator, it's 2. So still, the degree in the numerator is less than the degree of the denominator. Okay? So we call them proper rational functions. Okay? Of course, if the degree of the numerator is greater than the degree of the denominator, greater than or equal, we say that the rational function is improper. Okay? Now, if you have an improper rational function, what we're going to do is to divide, or what you need to do is to divide the function f by g. You can use long division. Okay? So when you divide it, your f of x over g of x, you will get some function q of x here. This function here will be a polynomial. Okay? So you have a polynomial plus you have r of x over g of x. Okay? Where this r of x, the degree of this will be less than the degree of g. Okay? So the degree of this r of x will be less than the degree of g. Meaning, when you divide f of x over g of x, where the degree of f of x is greater than or equal to g of x, what you will get is a polynomial plus a proper rational function. This is always the case if the degree of the numerator is greater than or equal to the degree of denominator. Okay? So, in this case, when we have improper um, function or rational function, we will always do this so that we will get a polynomial plus a proper function. And therefore, if we want to integrate this improper function, we'll just have to integrate this polynomial plus the integral of this proper function, proper rational function. And therefore, all throughout the discussion, we only need to consider proper function. Okay? We only need to consider proper function. And for the improper case, when you have the improper case, you do the division. Okay? So, for example, we want to integrate this. X cubed plus x plus 1 over x plus 1 dx. So, here we have a rational function. The degree in the numerator, it's 3. The degree in the denominator, it's 1. So, this is an improper rational expression. From this bullet, what we're going to do is to divide this x cubed plus x plus 1 divided by x plus 1. And I hope you still remember the long division. Okay? I hope you still remember the long division. So let us do that here. So you want to integrate x cubed plus x plus 1 divided by x plus 1 dx. This is a proper rational function. What I said earlier is to do the long division in order to get this expression here. You get a polynomial. It could be constant. Take note of that. Polynomials include constants. Okay? So you have to get a polynomial plus a rational function which is now proper. The degree of the numerator less than the degree of the denominator. So in here, you have x cubed plus x plus 1 divided by x plus 1. So I hope you still remember this. If not, listen very carefully. Okay? So what you do, you get from the dividend, you get the term that you want to divide. For example, this guy here, x cubed. And then divide it by the leading term in your divisor. So x cubed divided by x, that will just be x squared. And once you have that, you do multiplication. You do x squared times x plus 1. Okay? So if you do that, x squared plus times x, that will be x cubed. And then x squared times 1, you will have x squared. And then you subtract. Okay? When you subtract, of course, you will have here x cubed minus x cubed. That's just 0. And then you will have here, there is no x squared term in here. Okay? So it's just 0 minus x squared. You will have negative x squared. And of course, you have your x minus 0. So basically, you'll just bring this down as well as this constant here. Okay? Now, you check the difference. So this guy, you subtracted this. You will have a difference. Now, you look at the leading term after the subtraction. You check if the degree of the leading term is less than the degree of the divisor, the degree of your denominator here. If it is still greater than or equal, okay, you continue the division. So in here, you have degree 2, this one degree 1. So you continue the division. Same process. You divide minus x squared divided by x. And you will get here minus x. And then you multiply again. So minus x times x, that will be minus x squared. And then minus x times 1, that will be minus x. And then you do the subtraction again. So you subtract again. And you will see here, minus x squared minus negative x squared, that's just 0. And then you have x minus negative x, that becomes 2x. And then your 1 here minus, there's no constant here. So again, basically, that one goes down. Okay? And then, check again, you now have 2x plus 1. The degree is 1. It's the same as the degree of the denominator. So, continue the division. So now you have 2x divided by x. That will be positive 2. And then, you have positive 2, you multiply to x plus 1. So you will get 2x and then plus 2. And then you do the subtraction again. And if you do this, of course, 2x minus 2x, that's just 0. And then 1 minus 2, that's negative 1. Okay? You check the degree again here. You check the degree again here. The degree now it's 0. The degree of the divisor, it's 1. So the degree now is less than the degree of the divisor. Therefore, you stop the division. And therefore, you can now write this expression here as the integral of, this is your q of x, x squared minus x plus 2. And then you have this, minus 1 over x plus 1. And then the dx. Okay? Or before you write this, you can do the following. So after your long division in here, you will have x cubed plus x plus 1 over x plus 1. this is equal to x squared minus x plus 2 plus negative 1 over x plus 1. And of course, I'll just bring that negative 1 here. That's why we have minus d here. So this was, according to this, here, you have q of x and then plus r of x over g of x. So I just want to give the names. This is your quotient. Okay. This guy here, it's just this guy. This is the remainder. Okay. The remainder, it's just negative 1. Okay. But you write the whole expression here, negative 1 over x plus 1, because you cannot divide your negative 1 by x plus 1 anymore. Okay? And for completion, of course, you have this guy here, I've been calling it. So this is your dividend. And then this guy here, this is your divisor. Okay? So far, so good. So this expression was converted into this. We can now integrate this. You just have a polynomial, and here you have 1 over a linear expression. So if you do the integration, you'll just get x cubed over 3 minus x squared over 2 plus 2x minus ln absolute value of x plus 1 plus the arbitrary constant c. Okay? Questions? So on this example, we didn't do any partial fraction yet. We just did long division in here. Okay? So if you have rational functions which are improper, you do the long division. Okay? That's the first step. If you have rational functions with numerator greater, the degree of the numerator greater than or equal to the degree of denominator, do the long division. Okay? Unless, of course, you can factor the numerator and then factor the denominator, and maybe you can cancel something, etc. Okay? Now, suppose we only have the proper part. Okay? Suppose we only have the proper part. Okay? Of course, if we have only something like this, okay, we can immediately integrate that. But what if it's not that case? Okay? So let us consider case 1. So listen very carefully. For the case 1, suppose your denominator. Suppose your denominator, in this case, I'll write it as q of x. Suppose the denominator can be factored completely into distinct linear factors. So distinct linear factors. So a1x plus b1, it's different from a2x plus b2. It's different, okay? So it is possible that b1 is the same as b2. However, the a1 and a2 must be different. So the linear factor is still distinct. Okay? So suppose this is the case. Okay? Then, if you have a polynomial p of x and you divide it into q of x, assuming, again, assuming p of x here, the degree of p of x here is less than the degree of q of x. So let me write that. So in here, degree of p of x less than the degree of q of x. So assuming this, then p of x over q of x, it can be written this way. You have capital A sub 1 over a1x plus b1 plus capital A sub 2 over a2x plus b2 plus so on and so forth until you have capital A sub k over a sub kx plus bk. Okay? Where here, a1, a2 until ak, they are all constant. Okay? They are all constant. And therefore, if that's the case, you integrate this, you'll just integrate this sum here. And each term here in the sum is easily integrable. They are all ln. Okay? Let's do one example here. Suppose your original expression is x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x. Okay? So, practice factoring the denominator. Okay? When you try to factor this, you should end up with this product. You have x times 2x minus 1 times x plus 2. So you have three distinct expressions here, particularly linear expressions. Distinct linear expressions. So how do we proceed? How do we proceed? Once we know that, you will have x squared plus 2x minus 1 divided by x times 2x minus 1 times x plus 2. To this, according to this, okay, you'll just have some constant in the numerator and then denominator is a linear factor. So this guy here can be written as a over x plus b over 2x minus 1 plus c over x plus 2. Where a, b, and c here, you need to identify. Okay? Once you know the values of a, b, and c, if you integrate this, you'll just have to integrate this. And all of these are all ln after integrations. Okay? So how do we do that? From this step, you combine them again into a single expression. Of course, when you combine them, A, B, and C will be included in the expression. So if you combine them again, what you will get is the following. You will have A times 2x minus 1 times x plus 2 plus B times x plus 2 plus C times x times 2x minus 1. And of course, the denominator, it's just the product. X times 2x minus 1 times x plus 2. So what happened? since these denominators here, they are all distinct, all you need to do with the corresponding numerator, you multiply the other denominators. So you have a, this is over x, so you multiply the other denominators. That's why you have this. You have b here, the denominator is 2x minus y, 1. You multiply x and x plus 2. That's why you have this. Same goes with the c. Okay? And then from here, you can expand this. Okay? You can expand this if you want. And once you have expanded this, you can compare coefficients. Okay? You can compare coefficients. But for this case, since the denominators, the expressions are distinct, what we will do is just to assign values for x. That will help us solve for the values of a, b, and c. Okay? So again, what we're going to do is to assign values for x. Okay? That will help us solve the values of a, b, and c. So how do we do that? This expression here is equal to this expression. Their denominators, this guy and this guy, they are the same. So for this expression to be equal to this expression, the numerators must be equal. So you will have x squared plus 2x minus 1. This must be equal to a times 2x minus 1, x plus 2, plus b times x plus 2, plus c times x times 2x minus 1. Now, we choose the values for x properly so we can easily solve the values of a, b, and c. To do that, we will choose numbers or values for x that will eliminate a or b or both of them. Okay? And then we do also the same thing for solving b. And then we do the same thing for solving a. So just try to observe. This a has coefficient 2x minus 1. This c here has coefficient 2x minus 1. So if I let x to be equal to 1/2, then 2x minus 1, this will be equal to 0, correct? If you let your x equals 1/2, then 2 times 1/2, that's 1. 1 minus 1, that's equal to 0. So what will happen? If x equals 1/2, this will disappear. This will also disappear. And you are now left with b. Okay? So if x equals 1/2, on the left-hand side, you have 1/2 squared plus 2 times 1/2 minus 1. That's the left-hand side. For the right-hand side, this is 0. This is also 0. So you are left with b times 1/2 times 1/2 plus 2. And then you just simplify this. 1/2 squared, that's just 1/4. Okay? Of course, 2 times 1/2, that's 1. and then you have 1 minus 1, that's 0. So on the left-hand side, you'll just have 1/4. On the right-hand side, let us simplify first the product there. So you have here b times 1/2 times 1/2 plus 2. That's 5/2. Correct? So in here, you will just have b times 5/4, which gives us b equals 5. Sorry, it's not 5. B equals 1/5. Okay? Question so far? So we got our B. What about for A and for C? We do the same thing. We think of a number for which the B will disappear, the A will disappear, and we will get C. Or we think of a number that will make B and C disappear, and we will get A. Same process. Okay? So let me copy this first. So we have this. We already got B. Let's now solve for A. You see, we now let x equals 0. Okay? So we now let x equals 0. So in here, when x equals 0, the left-hand side, it's just -1. For the right-hand side, when x equals 0, this will be 0, this will be 0. So you'll just have a times -1 times 2. So this is just -2a. And therefore, we have a equals 1/2. Okay? And then, to solve for c, this guy here has factor x plus 2. This guy here has factor x plus 2. So, and this letter c here, we don't see any factor x plus 2. So if we let x equals -2, this will disappear, this will also disappear, and you have this. But when x equals -2, you have -2 squared plus 2 times -2 minus 1. This is equal to c times -2 times 2 times -2 minus 1. On the left-hand side, this is +4. This guy here, it's -4. So we'll be left with -1 again for the left-hand side here. For the right-hand side, let's simplify this. We have c times -2 times, in here, we have -4 minus 1, that's -5. So you will have here 10c, and therefore, RC, that's equal to -1/10. Okay? So, from here, we can now rewrite this. We use this, okay? And we will replace now the values for A, B, and C in here. Okay? So, this guy here, this is just equal to the integral. A was 1/2. So you have 1/2 over x. Then B was 1/5. The denominator for B, it's 2x minus 1. So plus 1/5 over 2x minus 1. And then C, it's negative 1 over 10. And the denominator was x plus 2. So we now have minus 1 over 10 over x minus, or x plus 2. And then you have the dx. And this guy, this expression here is easily integrable. So we'll just have 1/2 ln absolute value of x plus 1/5 ln absolute value of 2x minus 1 divided by 2 minus 1 over 10 ln absolute value of x plus 2 plus the arbitrary constant c. Okay? Question? Now, let us look at case number 2. Okay? For case number 2, suppose the denominator has a factor which is repeating. Okay? For example, there is a factor ax plus b, but it is repeated r times. Therefore, your q of x has a factor ax plus b to the r. Okay? So what will happen to this? What will happen to this? For this particular factor, okay, for this particular factor, you will do this. You will write the factors, okay, starting from ax plus b until ax plus b to the r. So you increase the power. They will be the denominators of the sum. Okay? And then the numerators will just be constants. Okay? So here, a1 over ax plus b plus a2, again, it's constant, over ax plus b squared, plus until the last factor, ax plus b to the r. The numerator is constant. Okay? So again, for case 1 here, if they are all distinct, you just write separately. Okay? For case 2, if there are repeating factors, you have the denominators all powers of the factor. Ax plus b, ax plus b squared, ax plus b cubed, until ax plus b to the r. And then the numerators, the corresponding numerators, they are just constant. A1, A2, etc. Okay? Let's try an example. So we want to integrate 4x over x cubed minus x squared minus x plus 1. So if you factor the denominator here, you will get x minus 1 squared times x plus 1. So you see here, Okay? The factor x minus 1, it is being squared. Okay? So the factor x minus 1, it is being squared. So, according to second case, the rational expression for x over x minus 1 squared, x plus 1, you can rewrite this as a over x minus 1 plus b over x minus 1 squared. That's for the factor x minus 1. So you write all the powers of x minus 1. And then for this factor, of course, you will still have c over x plus 1. Okay? Follow? And then you combine them again such that the denominator is x minus 1 squared, x plus 1. So if you try to combine them, of course, the denominator will be x minus 1 squared, x plus 1. But for the numerators, the denominator of a, it's x minus 1 only. But we need x minus 1 squared. So I am missing x minus 1. And we also need x plus 1. So I am missing x plus 1 in here. Then, the denominator for b, it's x minus 1 squared. I got this x minus 1 squared, but I am missing x plus 1. So I'll have to multiply x plus 1 to b. Then plus c. In here, the denominator is x plus 1. And then I have the x plus 1 here. The denominator, I am missing x minus 1 squared. So I'll multiply this with x minus 1 squared. Okay? So from here, you'll have the same. You'll just equate the numerator. Okay? Okay? So you will have for x, this is equal to a times x minus 1 times x plus 1 plus b times x plus 1 plus c times x minus 1 squared. So from here, we again assign values to x such that at least two of them will disappear. I mean, two of a, b, or c will disappear, and we will be able to solve the one that remained. So for here, this has factor x plus 1. This has factor x plus 1. So if we let, x equals negative 1, then left hand side we'll just get negative 4. The right hand side, this will disappear. This will also disappear. We'll just have c times negative 1 minus 1 quantity squared. This is c times negative 2 squared. And this is just 4c. And therefore, c, this is equal to negative 1. Now, when x equals positive 1. Left-hand side, it's just 4. Right-hand side, positive 1, so this will disappear. This guy here will disappear. So you will have b times 1 plus 1, or this is equal to 2b. And therefore, b, this is just 4 over 2, which is equal to 2. And now, you have values for c and b. However, b and c, we want to cancel them to get a. But b and c, for this part here and for this part here, they don't have any common factor. So they will not disappear at the same time. So what we will do is to use the values of b and c now, and then choose a value for x. Correct? So from here, okay, from this guy here, we now have for x equals a times x minus 1, x plus 1, okay, plus 2 times, that's the value of b, 2 times x plus 1, then plus the value of c, it's minus 1, so I'll put minus instead. So minus x minus 1 squared. So we are just left with a. Then we can now use any number again. Okay? But you don't use x equals 1 or negative 1, because if you do that, this will disappear. So you use other numbers. Let's just use x equals 0. When x equals 0, left-hand side, that's just 0. For the right-hand side, we have here a times negative 1 times positive 1 plus 2 times 1, okay, minus negative 1 squared. So here, you will have minus a, and then in here, negative 1 squared, that's positive 1. So you have 2 minus 1. So you will have plus 1. So this is 0 here. And this means that a is equal to 1. Okay? So now we have values for a, b, and c. And this is our expression here. We'll just have to substitute these values into this expression, and then we do the integral. Okay? So from here, you remember this, okay? And then the values are 1 to negative 1. So this guy now, it's equal to 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1 dx. Okay? So this guy here, this is just ln. This guy here, you can use power rule for integration. Well, of course, you need to do some substitution rule first. Okay? And then here, you have ln again. So let's just try to integrate 2 over x minus 1 squared dx. So like I said, you can let u be equal to x minus 1, du equals dx. So this is just 2 over u squared du. Or you can write this as integral of 2u raised to negative 2 du. So you will have 2 u raised to negative 1 over negative 1 plus some constant here, c sub 1. Then you bring back the x. Which means, so I'll put this is part of the solution, so I'll just write here aside. So in here, oops, we are now integrating. So we have now ln, absolute value of x minus 1. And then for this guy, we have this. So you will have minus 2 over x minus 1. And then for this, you have minus ln, absolute value of x plus 1 plus the arbitrary constant c. So this is the final answer. Okay? Questions? So again, recall, for case 1, if your denominator has linear factors and they are distinct, you just have constant over the linear factors, and then you add all of these. Okay? For case 2, if you have a linear factor which is repeating, okay, you will have to include all the powers of that linear factor. And then the numerator constant again. Okay? Let's go to case 3. Suppose your denominator has an irreducible quadratic factor. For example, you have ax squared plus bx plus c, where b squared minus 4ac is not equal to 0. Actually, is less than 0 in this case. Okay? In this case, that factor will have numerator a linear expression. So you have ax plus b in the numerator, and the denominator, you have that factor, ax squared plus bx plus c. Okay? So irreducible meaning you cannot factor this anymore. Okay? You cannot factor this anymore over the set of real numbers. Okay? So for that case, the discriminant, that value b squared minus 4ac is less than 0. So you won't be able to factor this over the set of real numbers. So again, for this particular factor of q, you have to put ax plus b in the numerator. And once you have this, you might need to recall 1 over k squared plus u squared du. That's equal to the tangent inverse. So 1 over k, tangent inverse of u over k plus c. Okay? Try to recall this. If your k is equal to 1, you'll just have tangent inverse of u plus c. But if k is not equal to 1, for example, it's something k squared, okay, you will get this guy here. If you don't believe this identity, you can solve this using your trigonometric substitution. Take note that this is of the form trigonometric substitution. So you can do that and you will end up with this. Okay? For example, let's have this. 2x squared minus x plus 4 over x cubed plus 4x. So you want to integrate that. Take note, numerator degree 2, denominator degree 3. So this is still a proper rational function. So we don't need to do long division. Now, looking at the denominator, okay, you can factor it into, so I'll write everything, integral of 2x squared minus x plus 4. For the denominator, you can factor x. What will remain inside is x squared plus 4. Then, of course, you have the dx. X squared plus 4, this is irreducible. But you see, you have a quadratic factor, you have a linear factor. So, if we do partial fractions, we have 2x squared minus x plus 4 divided by x times x squared plus 4. For the linear factor x, it's just constant over that linear factor. For the quadratic factor here, your numerator must be linear. So bx plus c over x squared plus 4. Okay? Questions? And then, the same process. The same process. You combine them again into a single rational expression. So x times x squared plus 4. And then you will have a times x squared plus 4 because the denominator of a is x. So I'm missing x squared plus 4. Then plus quantity bx plus c. The denominator of bx plus c, it's x squared plus 4. So I am missing the x. So this is multiplied to x. Okay? And then just like before, we can compare the numerators. You will have x squared minus x plus 4. This is equal to a times x squared plus 4 plus, in here, we have bx plus c times x. Now look at this. If your x equals 0, this guy here will disappear and you will be left with a. So if we let x equal 0, left-hand side, that's just 4. Right-hand side, you have a times 4. And this guy will disappear. Which means that a, this is equal to 1. We now have a value for a. But what about for b and c? So take note of this. There are no values for x for which this will become 0. There will be no real values for x for which x squared plus 4 will be 0. So what we're going to do well is to replace the a with 1. Okay? And therefore, we will get x squared plus 4 on this side. And then we'll just bring it to the other side. So that we'll be left with the expressions with b and c on the right-hand side. So what will happen? So we will have 2x squared minus x plus 4. This is equal to x squared plus 4. You look at that? Because a equals 1. And then plus, we have the bx plus c. Okay, let's just write that. Bx plus c multiplied to x. And then we bring this guy here to the other side. Okay, we bring this guy here to the other side. If we do that, well, you will get 2x squared minus x squared. So you'll just have x squared. And then here your 4 will be subtracted. Okay, so you will get 4 minus 4. So this will disappear. But you still have here the minus x. That's the left-hand side now. For the right-hand side, we'll just multiply the x. So what will happen is, we will get bx squared plus cx. So these two guys must be equal. The x squared minus x, it must be equal to bx squared minus or plus cx. But notice, you can just compare coefficients. The coefficient of x squared here, it's 1. The coefficient of x squared here, it's b. So for them to be the same, the coefficient b must also be equal to 1. That's just for the part of x squared. For the part of x, the coefficient of x here, it's negative 1. For this guy here, the coefficient is c. So for this expression, x squared minus 1 to be totally equal to bx squared plus cx, the c must be equal to negative 1. And since we already have b equals 1, we have the equality. Okay? So now we have all the values. Okay? So we are left to bring back this guy here. So this will be equal to the integral a over x. So we have 1 over x plus bx plus c. You will have x minus 1 over x squared plus 1. And then you have the dx. Sorry, should be x squared plus 4. Okay? And then for this guy, let us separate. So we will rewrite this as the integral of 1 over x plus x over x squared plus 4 minus 1 over x squared plus 4 quantity dx. Okay? So for this, suppose you don't know this identity. Well, I have not given this identity before, although it said recall. But anyway, you don't know this identity. In order to solve this part, you can use your trigonometric substitution. For this part, it's just ln. For this part, you can use u substitution. So let's do that. Let's put some work in here. We want to integrate x over x squared plus 4 dx. So for this, we let u be equal to x squared plus 4 du. This is equal to 2x dx. So this guy here, it will become 1/2 integral of du over u. So here you will have ln, or 1/2 ln absolute value of u plus c sub 1. And then you bring back your u here. Okay? And then for the other guy here, what you can do is the following. So look at this. What you can do is you want to integrate 1 over x squared plus 4 dx. You can factor out 4. You will have something like 1/4 dx x over 2 squared plus 1. That's how you're gonna prove this guy here. Actually, instead of doing that here, okay, instead of doing that here, let us prove the formula from before and let us apply it. Okay? So I'll do the formula, I'll use the formula here, but I'm gonna prove it. So in here, you have 1 over k squared plus u squared, and then you have du in here. Same method as in the other guy. We are going to factor 1 over k squared. And then what will remain is du over 1 plus u squared over k squared. Of course, if you multiply this k squared on this denominator, the k squared here will disappear. Or we'll rewrite this as 1 over k squared integral of du over 1 plus quantity u over k squared. And then we'll do some substitution here. We let t be equal to u over k dt. This is equal to du over k, or k dt. This is equal to du, which means we will have 1 over k squared integral du. It's k dt, and then for the denominator, this is just 1 plus t squared. And now you are more familiar with this. So if you bring this k out here, you'll just have 1 over k now, and then the integral of dt over 1 plus t squared, correct? Following? And therefore, we'll just have 1 over k tangent inverse of t plus c. But t, it's u over k. So you'll get 1 over k tangent inverse of u over k plus the arbitrary constant c. Okay? So take note, I just use u substitution or t substitution or the substitution rule here. But like I said earlier, you can use trigonometric substitution in here. And you will still get the same expression. So starting now, when you see something like this, for example, like this, you can use the formula. Therefore, if we continue from here, we will have ln of x, or ln of absolute value of x, plus this guy here, we have 1/2 ln absolute value of x squared plus 4. Okay? Then minus. Here you have 4, so that's 2 squared. So you have 1/2 tangent inverse of x over 2, and then plus the arbitrary constant c. And this is the final answer. Okay? Questions? Okay. Let's have another example for this. Suppose we have integral of 1 over x cubed minus 1. Here, you need to recall the factors for x cubed minus 1. But I'll write it here. X cubed minus 1 can be factored into x minus 1 times x squared plus x plus 1. And then you have the dx. Okay? Therefore, your 1 over x cubed minus 1, this will be equal to a over x minus 1 plus bx plus c over x squared plus x plus 1. And then we combine them again into a single expression. Denominator will be x minus 1 times x squared plus x plus 1. For the numerator, we'll have a times x squared plus x plus 1 plus bx plus c times x minus 1. So very similar process. We just compare the numerators. We'll just get 1 equals a x squared plus x plus 1 plus bx plus c times x minus 1. And then when we let x equals 1, this guy here will disappear. So we will have 1 minus or equals a times 1 plus 1 plus 1. This is equal to 3a. And therefore a equals 1/3. Okay? And then if we try other values, okay, this guy here will never be 0. So just like before, we'll just replace this a with 1/3. Okay? And then we try to solve for b and c. But unlike before, this is what we're going to do. So we now replace a with 1/3. So 1 equals 1/3 of x squared plus x plus 1. And then plus bx uh, bx plus c times x minus 1. So in here, look at this. If we let x equal 0, the b will disappear. So we will be left with c. Okay? So when x equals 0, left-hand side, that's just 1. Right-hand side, this is 0 plus 0 plus 1. So we'll have here 1/3 plus this guy here, it's 0. Here you have c times x minus 1. So 0 minus 1. So times negative 1. Okay? And therefore, if we solve for c, we will have c equals 1/3 minus 1. So I brought this side here, this guy here to the left-hand side. That becomes positive 1 now. And then here, I brought this to the right-hand side. So we have the minus 1 in here. So c will be equal to negative 2/3. And then to solve for b, we now have a value for a and a value for c. We'll use other numbers. We have here what? We used x equals 1. We also used x equals 0. So we use other numbers. Maybe let's use x equals negative 1. So so let me just write it here. When x equals negative 1, left-hand side, it's still 1. Right-hand side, we have 1/3 times negative 1 squared plus or minus 1 plus 1. And then plus quantity bx, where x equals negative 1. So that's minus b. And then plus c, but c, it's minus 2/3. So minus 2/3 here times x minus 1. So that will be minus 1 minus 1. So that's times minus 2. So let's just simplify things here. We will have 1 equals, in here you got positive 1 minus 1. That's 0 plus 1. That's 1. So we'll only get 1/3 in here. For this, we distribute the negative 2. So we'll get plus 2b plus, if you distribute that, you'll get 4/3. And therefore, we will get 2b plus 5/3. So you will have 2b equals 1 minus 5/3. This is negative 2/3. Or b equals negative 1/3. Okay? Any questions? So A, it's 1/3. B, it's negative 1/3. C, it's negative 2/3. So in here, we have the integral of the x over x minus 1, x squared plus x plus 1. We were able to decompose this into the integral of 1/3 over x minus 1. Correct? That's your a here. And then plus negative 1/3 x minus 2/3 over x squared plus x plus 1. And then you have the dx. And then in here, you can factor out negative 1/3 for this guy here. So if we try to rewrite that, well, let's integrate this part here. It's easily integrable. So you will get ln, or 1/3 ln absolute value of x minus 1. And then in here, you factor out negative 1/3, and you will have the integral x plus 2 in the numerator. In the denominator, you have x squared plus x plus 1. And then you have the dx. Okay? And then you integrate this guy here. Okay? Let us integrate this. Let's separate the solution for that. So you want to integrate x plus 2 over x squared plus x plus 1 dx. Here's what we're going to do. We separate the two guys. Okay? So this will be equal to integral of x over x squared plus x plus 1 dx plus integral of 2 over x squared plus x plus 1 dx. Okay? For this part here, I'll do some trick. Notice that if we let u to be equal to x squared plus x plus 1, du will be 2x plus 1 dx. Correct? But this guy here, it's just x. So from here, I will produce this 2x plus 1. So what I'm going to do, first, I'll multiply both the numerator and denominator by 2. So what will happen is I will have 1/2 integral of 2x. Correct? And then same denominator. You have x squared plus x plus 1 dx plus, of course, this is still integral of 2 dx over the denominator here. Okay? Now, for this denominator on this side, you look at this. Okay, I'll continue first with this guy. So let us focus first on this guy. Then I'll work on this guy after I have produced this 2x minus or 2x plus 1. So you see what I did first? Okay. I have the 2x. I have initially the x. I multiplied 2. I have to divide 2. So I won't change anything. Correct? So I did not change anything from this up to this. Now, I want the plus 1. So what I'm going to do is to add 1. But now I am changing the expression. To bring back the original expression, I'll subtract the 1 again. Okay? Again, from this expression, I have x over x squared plus x plus 1. From here, from the x in the numerator, I want to produce 2x plus 1. So the first step, I'll multiply x with 2, but I'll divide it by 2 again. That's why you see the 1/2. To produce the plus 1, I'll add 1 and subtract 1. So I added 0, essentially. Okay? And now we have this. So what we're going to do next is to separate this 2x plus 1 from the minus 1. Okay? So what I'll get is equals 1/2 integral 2x plus 1 over x squared plus x plus 1 dx minus 1/2 integral of dx over x squared plus x plus 1. So this guy here, it came from this minus 1 times that 1/2. That's why you still have this 1/2 and the minus in here. And then you still have this. Anyway, let's write that x squared plus x plus 1. So you still have this integral of 2 dx x squared plus x plus 1. And look at this. Okay? You have here 1/2. You have negative 1/2 plus 2. So if you combine this expression, you'll end up with 1/2. So this is just the same as this guy here. Whereas for this, you have 2 minus 1/2. That's 3/2. So plus 3/2 integral of dx over x squared plus x plus 1. So for this guy, I can do this U substitution here. Now, what about this guy? What I'm going to do is to rewrite this x squared plus x plus 1 into either sum of two squares or difference of two squares. And we will use trigonometric substitution there. I will write this as something in square plus or minus constant squared. Okay? To do that, Note that your x squared plus x plus 1, okay? If you look at only x squared plus x, and you want to write this as something x plus, say, a squared, what should be this guy here? Of course, it should be a plus, but what should be this guy here? If you expanded this guy here, you will get x squared plus 2ax plus a squared. 2a, coefficient of x here. The coefficient of x here, it's 1. So what does that mean? 2a, this is equal to 1. A equals 1 half. So for this guy here, it should be 1 half. But what should be this part here? That's your a squared. So a squared, this is equal to 1/4. And therefore, using these facts, this is x squared plus x plus 1/4 plus 3/4. And now this guy here, it's precisely this, which is this guy. Okay? You will get x plus 1/2 quantity squared plus 3/4. That will be the denominator here. And therefore, you will have something squared plus this guy here squared. Okay? So what about that now? This guy here equals, I have the 1/3 ln absolute value of x minus 1. Then minus 1/3 quantity. You write this. Okay? So I think I'll adjust. I will need some space here. So I have 1/3 times this guy here. It's just 1/2 integral of 2x plus 1 over x squared plus x plus 1 dx. Then plus 3/2 integral of dx over quantity x plus 1/2 squared plus 3/4. And then close parenthesis here. Okay? Therefore, this guy here, it's just this u substitution. So this becomes ln of the absolute value of x squared plus x plus 1. This guy here, it's tangent substitution. Or you can use the formula that we had earlier. But instead of u, you have x plus 1/2. Okay? So from here, u, that's x plus 1 half. So if you get your du, that's just dx. So you got this du here. This guy here will be u, and this will be your k squared. Correct? Therefore, this guy here, it's just 3 halves times 1 over k. This is your k. So this will be 2 over square root of 3. Then tangent inverse of u, but u it's just x plus 1 half divided by square root of 3 over 2. So let me enlarge this parenthesis here. This is square root of 3 over 2. And then you have d plus c. And this is the final answer. Okay? So look, although the integral here, it looks simple. 1 over x cubed minus 1. It's really, really simple. But the solution, it takes a lot of work. Okay? So this is for case number 3. For case number 4, what if the quadratic factor is repeating? Same as with case number 2. When you have a linear factor which is repeating. So for this case number 4, you'll do the same thing as in the linear case, the case number 2. The numerator, all of them will also be linear. Okay? Okay? So let's do this example here. You have this. You have the integral of 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 squared. So this expression here can be decomposed into this guy. Okay? So you can see there's just 1 over x. Then here you have denominator x squared plus 1. And then here you see denominator x squared plus 1 squared. You see that? X squared plus 1, it's a repeating quadratic factor. That's why you have the x squared plus 1 and then the x squared plus 1 squared. But let us do that. Let us just derive this guy here. Okay? So you will have 1 minus x plus 2x squared minus x cubed divided by x times x squared plus 1 squared. So according to case 4, and we also include case 1, this guy here can be written as a over x plus, for the denominator, x squared plus 1, let's just write bx plus c. So numerator is linear. Plus, because x squared plus 1 is a repeating factor, we include all powers. So you have x squared plus 1 quantity squared. But the numerator is still linear. So this will be dx plus e. Okay? So that's what it meant. So this guy here, it's coming from this decomposition. Okay? And then you do the same process. You solve for the values of A, B, C, D, E. And according to this, you will get all these values. So if we combine into a single um, rational expression, the denominator will just be x times x squared plus 1 quantity squared. And then we have A here. The denominator of A, it's just x. So I am missing x squared plus 1 squared. And then plus bx plus c. The denominator of bx plus c, it's just x squared plus 1. So I am missing x, and I am also missing one of the x squared plus 1. So I'll have x times x squared plus 1. And then finally, for the dx plus e, the denominator, it's x squared plus 1 squared. I have that here, but I am missing x. So I'll just have x here. And then from here, you compare numerators, then you solve for A, B, C, and D. E, including E. Okay? So I'll leave the rest to you. Okay? There should be no equal sign here. But anyway, I leave the rest to you to get these values.